You look at your hand, it seems solid. You tap it on a table, it feels solid. The world around you feels real. It has depth. It has 3 dimensions: length, width, height. You can move forward, backward, left, right, up, down. This is the world you know. It's reality. But what if it's not? What if this solid 3D world is an illusion? Not an illusion in the sense that it isn't real. It's very real. You're really here. But what if the fundamental reality is different? What if all the information that makes up you, the table, the earth, the entire universe, is actually encoded on a distant, flat, 2-dimensional surface? What if our 3-dimensional existence is just a projection, like a hologram? This sounds like science fiction. This sounds like something from a movie. And for a long time, it was mostly just a wild idea. But in the world of theoretical physics, it's become a serious and important concept. It's called the holographic principle. It's an idea that grew out of the deepest mysteries of the universe, from the study of things so extreme they break our understanding of physics. It grew from black holes. To understand the holographic universe, you have to start with black holes. Black holes are regions of space where gravity is so strong that nothing can escape. Not even light. They form when massive stars die and collapse under their own weight. They create a point of infinite density called a singularity, and around it, a boundary called the event horizon. Once you cross the event horizon, there's no coming back. It's the ultimate one-way street. For decades, physicists thought they understood the basics of black holes. They had Einstein's theory of general relativity to describe gravity and the warped space-time around them. But then Stephen Hawking came along and threw a wrench in the works. He realized that when you mix the laws of gravity with the laws of quantum mechanics, the strange rules that govern the tiny world of particles, black holes do something unexpected. They're not completely black, they glow. It's a very faint glow called Hawking radiation. Over immense periods of time, this radiation causes the black hole to lose mass. It slowly evaporates. A black hole the mass of our sun would take an absurdly long time to evaporate, far longer than the current age of the universe. But eventually, given enough time, any black hole will radiate away its energy and disappear in a final puff of radiation. This created a huge problem, a paradox. It's called the black hole information paradox. In physics, there's a fundamental rule: information can never be destroyed. Information is just the specific arrangement of particles. It's the details. Think about burning a piece of paper. You might think the information on it, the words, is gone. But it's not. In theory, if you could collect every single particle of smoke, ash, heat, and light that resulted from the fire, you could reconstruct the original piece of paper. The information is just scrambled, not erased. This principle of information conservation is a pillar of modern physics. But Hawking's discovery seemed to violate it. Imagine you throw a book into a black hole. The book contains information, the specific arrangement of its atoms, the story in its pages. The black hole gets a little bit bigger. Then, over eons, the black hole evaporates. The Hawking radiation that comes out is random. It's thermal. It contains no information about what fell in. It only knows the black hole's mass, spin, and charge. It doesn't know if an encyclopedia or a pile of dust fell in. So, when the black hole is completely gone, where did the information in the book go? It seems to have been completely erased from the universe. This was a crisis. It meant that either quantum mechanics or general relativity, our two best theories of the universe, had to be wrong. Physicists fought over this for years. Hawking himself was convinced the information was lost. Others, like the Dutch physicist Gerard Dint Hooft, were not. They believed the information had to be preserved somehow. This is where the hologram idea was born. Dint Hooft, and later an American physicist named Leonard Susskind, came up with a radical solution. They proposed that the information never actually makes it inside the black hole. When the book falls toward the black hole, from our perspective, it seems to cross the event horizon and disappear. But according to their idea, the information contained in the book gets imprinted, or encoded, onto the event horizon itself. It gets smeared across the 2-dimensional surface of the black hole. Think of it like this. The event horizon is a 2D surface that contains all the information about the 3D stuff that fell into it. The information isn't lost, it's just stored in a different way, on a lower dimensional surface. When the black hole evaporates, the Hawking radiation carries this information away, bit by bit. It's not random, after all. It's incredibly scrambled, but the information is still there. The book isn't gone. Its essence is painted on the surface and then slowly released. This was a mind-bending proposal. It meant that a 3-dimensional object, the black hole's interior, could be completely described by the physics happening on its 2-dimensional boundary. The amount of information you can store inside a region of space is not proportional to its volume, as you might expect. It's proportional to its surface area. This is the holographic principle. Just like a 2D piece of film can contain all the information to project a 3D hologram, the 2D surface of a black hole could contain all the information for its 3D interior. So, this strange idea seemed to solve the black hole information paradox. It was a neat trick for saving the laws of physics from breaking down at the edge of a black hole. But then Don Hooft and Susskind took it a step further. They asked a much bigger question. If this principle applies to a black hole, which is just a region of space-time, why not apply it to the entire universe? The idea is that our entire three-dimensional universe could be a projection of information stored on a two-dimensional surface at the very edge of the cosmos. This distant boundary contains all the data needed to create the illusion of our reality. The world we experience, with its 3 dimensions of space and 1 of time, might be the hologram. The real fundamental reality would be a flatter, simpler, lower-dimensional system written on the cosmic horizon. What is this boundary? It's not a physical wall you can go and touch. It's a theoretical surface infinitely far away. It's the boundary of our observable universe. The physics happening on that surface would be described by a different set of rules, probably a type of quantum field theory without gravity. But the physics of that flat reality would somehow give rise to everything we see and experience here in the book of 3D space, including the force of gravity itself. In this view, gravity is not a fundamental force. It's more like an emergent phenomenon. A thermodynamic effect, like temperature or pressure. Temperature feels real, but it's just the average motion of a bunch of tiny atoms. Well, you can't have temperature with just one atom. It only emerges from the collective behavior of many. Similarly, in the holographic universe, gravity might not be part of the fundamental 2D physics on the boundary. It would emerge like a phantom force as part of the 3D holographic projection. This was an incredible, almost unbelievable idea, okay? For a while, it was just speculation. It was a cool concept, but there was no mathematical proof. There was no way to connect a universe with gravity to a universe without it. It was like having a dictionary to translate between 2 languages, but you only have the words for one of them. You can't prove they're describing the same thing. Then, in 1997, a physicist named Juan Maldacena had a breakthrough. He found the dictionary. He was working in the context of string theory, which is one of the leading attempts to unite gravity and quantum mechanics. String theory proposes that fundamental particles are not points, but tiny, vibrating strings. It also requires the existence of extra dimensions of space. Maldacena discovered a precise mathematical relationship, a duality, between 2 very different-looking theoretical universes. One was a 5-dimensional universe with gravity, a lot like ours, but with an extra dimension and a weird curved geometry. This universe is called anti-de Sitter space, or ADS for short. The other universe was a 4-dimensional one living on the boundary of the first one. This boundary universe was flat, governed by quantum field theory, and had no gravity. This is called a conformal field theory, or CFT. What Maldacena showed was that these 2 universes were mathematically equivalent. Anything that happens in the 5D universe with gravity has a corresponding description in the 4D universe without gravity on its boundary. They are 2 different ways of describing the exact same physics. A complex problem involving gravity in the 5D bulk could be translated into a simpler problem without gravity in the 4D boundary, solved there, and then translated back. This was huge. It was the first concrete mathematical example of the holographic principle at work. It wasn't just a vague idea anymore, it was a working model. It was like finding a Rosetta Stone that connected the language of gravity with the language of quantum particles. The ADAS-CFT correspondence, as it's now known, became one of the most important discoveries in theoretical physics in the last few decades. It gave physicists a powerful new tool. They could now study the intractable problems of quantum gravity by looking at their simpler holographic duals. But there's a catch. A big one. Maldacena's model is a toy universe. It's not our universe. Our universe is not anti-de Sitter space. It has a different geometry. It's expanding, and the expansion is accelerating. The ADAS space in the model is static and has a different kind of curvature. So, while the ADAS-CFT correspondence proves that a holographic universe is mathematically possible, it doesn't prove that our universe is a hologram. It's a proof of concept, not a proof of reality. Still, it was enough to make many physicists take the idea very seriously. If the principle works in one type of universe, it's plausible it could work in others, including our own. The challenge is figuring out what the holographic description of our universe would look like. We don't have the dictionary for our specific cosmos yet, so this is a beautiful theoretical idea. It potentially solves deep problems in physics and provides a new way to think about reality. But is there any way to test it? Can we find any evidence that we are living in a hologram? If our universe is a projection, then our reality should have a finite resolution. Just like a digital picture is made of pixels, a holographic universe should be made of fundamental units of information, tiny bits of space-time. You can't zoom in forever and see a perfectly smooth reality. At some incredibly small scale, the Planck scale, which is a trillion times smaller than an atom, the smoothness should break down. Space-time itself should be grainy. This graininess would be the ultimate pixelation of our universe. Finding it would be direct evidence for the holographic principle, but the Planck scale is so small that we have no hope of probing it directly with any particle accelerator we could ever build. However, some scientists thought there might be another way. If space-time is fundamentally blurry at this tiny scale, maybe that blurriness could be detected. Even if the pixels are too small to see, their collective effect might create a kind of fundamental noise or jitter in the fabric of reality itself. This led to an experiment at Fermilab called the holometer. It was designed to be the most sensitive measurement of distance ever made. The idea was to use two powerful laser interferometers placed close to each other. These devices are extremely good at detecting tiny changes in position. The holometer was looking for a specific type of noise, a holographic noise that would cause space-time itself to jiggle randomly at a certain frequency. If this jiggle were detected, and it correlated between the two interferometers, it would mean that space itself is not a fixed, stable background. It would mean that information about position is limited, just as the holographic principle predicts. The experiment ran for about a year. It was an incredible feat of engineering. And the result? Nothing. It found no evidence of the holographic noise it was looking for. The universe at the level the holometer can measure seems to be perfectly smooth. This was a disappointment for proponents of some simple holographic models, but it didn't kill the idea. It only ruled out a specific version of it. The holographic graininess could be of a different type, or at a smaller scale than the holometer was designed to detect. The experiment's failure didn't disprove the principle, it just proved one branch of the theoretical tree. There have been other attempts to find evidence. Some researchers have looked for signs of it in the cosmic microwave background CMB, the faint afterglow of the Big Bang. They've analyzed the patterns in this ancient light, looking for anomalies that might be better explained by a 2D holographic model of the early universe than by the standard 3D model. Some studies have claimed to find a slightly better fit with a holographic model, but the results are far from conclusive. The evidence is weak and highly debated. So, at the moment, we are left with a powerful, elegant idea that solves some deep theoretical problems, but with no solid experimental evidence to back it up. It remains on the frontier of physics, a compelling possibility that we don't yet know how to prove or disprove. But let's imagine for a moment that it's true. Let's say we find proof tomorrow. What would that actually mean for us? Would it change anything about our lives? First, it's important to understand what it doesn't mean. It doesn't mean we are not real. Your pain when you stub your toe is real. The chair you're sitting on is real. The sun in the sky is real. A hologram is still a real physical phenomenon. The 3D image projected from a 2D film is a real image made of real light that you can see and interact with. If our universe is a hologram, it is a perfectly functioning, physically real one, governed by consistent laws. Our experiences would be no less valid. The universe would be just as real as it ever was. What would change is our fundamental understanding of what that reality is made of. It would mean that space as we perceive it is not fundamental. We think of space as the empty stage on which the play of the universe unfolds. But in a holographic world, space itself is part of the play. It's an emergent property of the more fundamental information living on the boundary. The true reality is the information. The 3D space we live in is just how our minds and our physical laws interpret that information. This could have profound implications for some of the biggest puzzles in physics. For example, it could explain the weirdness of quantum entanglement. This is the phenomenon Einstein called spooky action at a distance, where two particles can be linked in such a way that measuring one instantly affects the other, no matter how far apart they are. In our 3D space, this seems to violate the rule that nothing can travel faster than light. But in a holographic universe, there might be a simple explanation. Two particles that are very far apart in our 3D projection could actually be right next to each other on the 2D surface where the fundamental information lives. The spooky connection isn't spooky at all. It just looks that way from our limited, projected perspective. What we see as a vast distance in the hologram is not a real distance in the underlying reality. This leads to another common question. If we live in a hologram, does that mean we're in a computer simulation? This is a popular idea, but it's a confusion of two different concepts. The holographic principle is a proposed law of nature about how information is organized in the cosmos. It doesn't say anything about who or what created that information or why. It just says that the universe can be described by information on a boundary. A simulation, on the other hand, implies a simulator. It implies intent. It suggests that some intelligence built a computer and is running our universe as a program. The holographic principle doesn't require this. The universe could be a natural hologram, just as a rock is a natural object. There's no programmer needed. The laws of physics themselves could be the projector. That said, the idea that reality is fundamentally information does make the simulation hypothesis seem a little less crazy than it otherwise would. If the universe is fundamentally bits of information, it's not a huge leap to imagine those bits being processed by something. But it's a philosophical leap, not a scientific one. Ultimately, the question of whether our universe is a hologram forces us to confront our most basic assumptions about reality. We experience a world of 3 dimensions. We feel like we move through a pre-existing space. The holographic principle suggests this is an illusion. The fundamental reality is a flat world of quantum fields, and everything we know, including the dimension of depth, and even gravity itself, is a grand emergent projection. The search for an answer continues. Physicists are trying to build more realistic holographic models that match our universe. They are looking for new ways to test the idea, perhaps by studying gravitational waves or the details of the cosmic microwave background with greater precision. We may one day find the cosmic pixels that prove our world is a projection, or we may find evidence that firmly refutes it. For now, we live with the uncertainty. We live inside this magnificent, complex, 3-dimensional world, while some of our best minds are telling us it might all be an elaborate show, projected from the edge of reality. It's a humbling thought. It reminds us that our perception of the world is limited. What feels solid and real might just be a shadow of a different, stranger truth. The hand you look at is still your hand. The table is still a table. But the story of what they truly are at the deepest level of reality might be far stranger and more beautiful than we ever imagined. The universe might not be what it seems, and the quest to find out is what science is all about.